is Ocula, a neural network to detect the severity of diabetic retinopathy for early prognosis of diabetes. 415 million people across the world have diabetes. This ranges from those in developing countries as well as developed. Diabetes is a worldwide epidemic, and currently the only solution is detection and not cure. Therefore, it is crucial that we find an early and affordable diabetes detection solution. And diabetic retinopathy is a disease which can lead to vision impairment and even blindness. It is the precursor for both diabetes as well as glaucoma. There is a clear connection between diabetic retinopathy and diabetes. So if I can create an innovation that detects diabetic retinopathy, it can show if one is at risk for diabetes. But what are the issues with current solutions? For diabetes, it is a blood or urine test, both of which only occur after the patient is at high risk for diabetes. For diabetic retinopathy, a clinician has to manually go through and identify signs of DR, which is not only time-consuming, but can have human error. So my problem was the lack of access to an early and affordable diabetes detection solution. And my solution was to create a neural network that can detect the severity of diabetic retinopathy for early prognosis of diabetes. During this stage, I also created some design success criteria to help ensure whether or not my device is successful or not when actually applied. Some of these criteria were having an accuracy greater than 90%, a use of a 25-layer network, and being able to classify the 5 stages of retinopathy correctly as well as quickly. And so I started off my project with the collection and validation of retinal images. I worked with the California Healthcare Foundation and the IPAX organization for retinopathy screening to do so. I gained about 35,000 retinal or fundus images, which showed high definition of DR or no DR, based on the 5 stages. These images were also vetted by ophthalmologists, which means they were reliable to use. The data had also been pre-classified into the 5 stages of diabetic retinopathy, with 0 being no signs and 5 being severe swellings in the blood vessels and a high risk of retinal detachment, which leads to permanent blindness. The goal of this network and innovation was to find diabetic retinopathy when it was at the earlier stages, such as 2 or 1, which can allow people to still have a good personal health lifestyle while still making sure that they're taking care of their diabetes. I then moved on to the resizing and noise removal of images. These images had come from many different sources and they were all in different sizes. So I resized them all to the vector of 227 by 227 with 3 RGB channels. The images also had a lot of noise because they came from different sources. So I performed a median filter to show the difference between the two. Here you can see a before and an after image using the median filter. There's a clear version of higher definition, and it'll be easier for the neural network to focus on the image instead of background clutter. I then extracted certain features for my device to focus on. These images ranged from something such as exudate areas to micrometers. They all were the most common signs of diabetic retinopathy, which can be identified on this image. These images were also crucial because they had the 5 features clearly outlined, and I had to train my network on these images to teach it which ones were actually diabetic or not. Moving on to the creation of the actual neural network. I created a 25-layer neural network with 9 different types of layers. Image input, where the images are inputted, convolution, where features are extracted, rectified linear unit, which helps to speed up the gradient process, max pooling, where downsampling occurs, a dropout layer, which prevents overfitting, a fully connected layer, which aligns features to categories, softmax, where input data becomes raw data, and classification, where raw data is properly classified. I then had to select an algorithm for this network. I tested multiple algorithms and immediately eliminated some, such as polynomial, linear, or random true forest, because they would not fit this heavily convex solution. I, in the end, had to come down to gradient descent or stochastic gradient descent. I chose stochastic gradient descent as it allowed for the ebbs and flows of accuracy, whereas gradient descent assumed that there was one perfect bowl shape with the highest accuracy point there. I knew this could not be true in a neural network, so stochastic gradient descent was chosen. Moving on to the selection of the learning rate. The learning rate determines the size of the steps the program will take from one point to another on the network. Too large means that the optimum point is missed, but too small means that the program gets stuck in a certain valley. In the end, I chose a learning rate of 0.01 as it had a high accuracy but a low training time. It was also the best solution of the multiple learning rates tested. Now it was time to gather everything and train my network. I utilized all of these best components and trained the network. As you can see, accuracy clearly went up and loss went down as more and more epochs progressed. This shows that my network was able to clearly pick up on how and what features to focus on. After the network was trained, I moved on to prediction. Prediction was where I gave the network images it had not seen before and asked it to properly identify them into the 5 stages. My network had an average accuracy of about 92.5% and a precision of about 91.7%. In the confusion matrix, it's clearly identifiable that I was able to accurately classify the 5 stages of retinopathy. However, there is more of a correlation on 0 because I had more signs of 0 diabetic retinopathy. Now, this is a good innovation. With 91% accuracy, it is clearly ready for the world. However, I still wish to improve it because no innovation is fully completed without more tweaking. So for further improvements, I wish to increase accuracy by increasing the amount of images I have, especially in the higher stages of diabetic retinopathy. I want to broaden the amount of diseases and increase versatility by moving into other eye diseases such as drusen, DMV, etc. I also want to move from a single CPU to GPU for faster processing, increased efficiency, as well as increased accuracy. As for further developments of Ocula, I wish to create a mobile app which is connected to certain kiosks or even an Arduino-based fundus camera so that people can get real-time results of their eyes and of their diabetic progression. With this Arduino fundus camera, the app, and kiosks, I truly believe that we can change the world with Ocula, simply one eye at a time. Thank you so much for giving me this opportunity to share Ocula with the world, and I truly believe and I truly hope to work with you on moving forward with this project. Thank you.